Greetings everyone and welcome back to our online lecture series for CHE 2300. In today's lecture video we are going to be going through an example heat transfer problem. This example problem will hopefully help tie together some of the concepts and equations that you've been introduced to over the past couple of lecture videos related to forced heat convection. This example problem is also nice because it will allow me to introduce a couple of new equations that will be helpful moving forward when solving heat transfer problems. So I have my screen set up in such a manner that if you need to pause the video right now, draw the schematic, copy down all of the information that you see before moving forward, please do so. I'm going to describe the problem and move forward afterwards. Okay, so what you see in front of you is what is called a double pipe heat exchanger. This is known as a double pipe heat exchanger because it consists of two pipes, an inner and an outer pipe. You can think of it as an inner tube and an outer jacket. So inside the inner tube we have benzene that is flowing at a velocity of 5 feet per second. It enters our double pipe heat exchanger at a temperature of 141 degrees Fahrenheit and exits the heat exchanger at a temperature of 79 degrees Fahrenheit. We have water that enters the jacket of our heat exchanger at a temperature of 65 degrees Fahrenheit and exits the heat exchanger at a temperature of 75 degrees Fahrenheit. You'll see in the title that I have the word countercurrent. This is called a countercurrent heat exchanger, or this heat exchanger is being operated in a countercurrent configuration because I have my hot fluid, in this case my benzene. This is my hot fluid, entering the heat exchanger in a different and flowing in a different direction than my cold fluid or my water. Right, so this is the first place that I'm going to introduce a new concept or equation. So when we talk about heat exchangers, oftentimes we will talk about the temperature difference in our heat exchanger in terms of a log mean temperature difference. And so if we label, let's do this in a different color so it stands out. We're going to label the entrance of our heat exchanger as A, the exit of our heat exchanger as B. The log mean temperature difference of my heat exchanger that is defined as delta T log mean, the difference in approach temperatures on one side of my heat exchanger. In this case, I'm going to write it as the exit minus the approach temperatures, or different approach temperature, at the entrance of my heat exchanger, divided by the natural log of the ratio of those two quantities. So first thing, what do I mean by approach temperature? What I mean by approach temperature is the difference in temperatures on either side of the heat exchanger. So the approach temperature on the entrance of my heat exchanger would be the temperature difference between those two streams. And the temperature difference at the exit, or approach temperature of the exit of my heat exchanger, is going to be the temperature difference between those two streams. So for this particular example, my log mean temperature difference is going to be 141 minus 75 minus 79 minus 65. divided by the natural log of 141 minus 75 divided by 79 minus 65. This results in a log mean temperature difference of 33.5 degrees Fahrenheit for this particular heat exchanger. Much like you saw with the log mean area, we define a log mean temperature difference because the driving force in terms of temperature difference is not always constant across our heat exchanger. And I don't want to talk about that too much because we'll talk about that or get into that a little bit more when we're talking or get into more detail involving heat exchange equipment. Right? But for now, just know that there is a thing called the log mean temperature difference, and it helps to describe the driving force for heat transfer in my heat exchange equipment. Okay, so back to our example problem. Benzene enters on one side of our heat exchanger. Our cooling fluid water enters on the other side of the heat exchanger. The inner pipe is a 7/8 inch BWG 16 copper. BWG is Birmingham wire gauge. It is analogous to the Schedule 40. Right? It is some type of system for naming pipes. In this particular case, the system for naming copper pipes. So there is an appendix in your book similar to an appendix that you have for the Schedule 40 and Schedule 80 steel pipes for BWG copper pipes. So the information that we get, I'll just go ahead and write that down. I believe here this comes from Appendix 4. And the information we're going to get for our outer pipe, which is 1 1/2 inch Schedule 40 steel, is going to be from Appendix 3. Go back to a black color. And the problem here asks me to determine the convective heat transfer coefficient on the inside of my pipe, convective heat transfer coefficient on the outside of my inner pipe, and the overall heat transfer coefficient based on the outside surface area of the inner pipe. Okay, we are given the velocity for our benzene, so we can calculate a Reynolds number. Based on that Reynolds number, it will tell us what our flow regime is for our fluid and allow us to select the proper heat transfer equation to calculate our convective heat transfer coefficients. Unfortunately, we are not given any information about the velocity of the water, so we are going to have to determine that based on a heat balance in our system. So the first thing we're going to do is determine the bulk temperature of both our benzene and our water. So the bulk temperature for our water is going to be equal to 65 plus 75 divided by 2. Which is equal to 70 degrees Fahrenheit. And the bulk temperature of our benzene, it enters at 141, it exits at 79. That gives me a bulk temperature of 110 degrees Fahrenheit. And so you'll see already in the table on the left, already in the table on the right, we have parameters at our bulk temperature for both the benzene and the water, because we will need those to help calculate both our Reynolds number and our Prandtl number. Okay, now that we have our bulk temperature, the next thing we want to attack is that velocity. We want to calculate the velocity of our cooling fluid. let me go ahead. So let's make a couple of assumptions here. Let's make an assumption here. We are going to have adiabatic heat transfer, meaning all heat lost by the benzene stream is gained by the water. By making this assumption, we can use a heat balance to calculate the mass flow rate of our water, and then based on the cross-sectional area and the density of our water, we can calculate the average velocity of that cooling fluid. Okay, our inner pipe, and again I'm grabbing this information from Appendix 4. The diameter of our inner tube is equal to 0.0621 feet. We can also get the cross-sectional area of our inner tube from that same appendix. We get a value of 3.03 times 10 to the negative 2 feet squared. Our outer jacket, which is our Schedule 40 steel, we're told that that is 1 1/2 inch. Based on that, we have a diameter on the inside of our jacket equal to 0.1342 feet. Okay. So based on our assumption of adiabatic heat transfer, we know that the heat flow of our benzene is equal to the heat flow of the water. Technically, if we're going to indicate a direction here, it's leaving the benzene. The heat is leaving the benzene and flowing into the water. Okay, we know that Q dot is equal to M dot CP delta T. We also know that M dot is equal to the average velocity times the density times the cross-sectional area. So if we do this calculation for the benzene, we can calculate the mass flow rate of benzene. That is equal to our 5 feet per second multiplied by the density of the benzene at our bulk temperature, which is 53.1 pound mass per foot cube. 53.1 pound mass per foot cubed, and then we have our cross-sectional area of the inner pipe, which is 0.00303 feet squared. This gives us a mass flow rate of our benzene equal to 0.804 pound mass per second. Now that we have our mass flow rate of our benzene, we know the temperature drop of our benzene, we know the specific heat of our benzene, we can calculate the heat flow from the benzene, which we can then use right here on the other side, because we know that the Q dot of our water is going to be equal to the mass flow rate of our water times the specific heat multiplied by the temperature increase of the water. So let's go ahead and do that. We have 0.804 pound mass per second. That is multiplied by the specific heat, which is 0.435 BTUs per pound mass per degree Fahrenheit. And then I'm going to multiply that by the temperature drop of our benzene stream. Hopefully I've done my algebra correctly, and I end up with 21.7 BTUs per second for the heat flow from the benzene, which we are going to assume is equal to the heat flow into the water. Okay, so then we take our 21.7 BTUs per second. That is equal to m dot water multiplied by the specific heat of our water, which is 1 BTU per pound mass degrees Fahrenheit, and then the temperature drop of our water, temperature increase, we're going to write it as a temperature drop. I could make this a negative, but I'll just leave it as a positive and switch my temperatures around. Solving that equation for the mass flow rate of water, I get a mass flow rate of 2.168 pound mass per second. Okay, now I need to calculate, now I need to use this mass flow rate to calculate my average velocity. All right, keeping in mind here that the water is flowing in the outer jacket of my double pipe heat exchanger. So the cross-sectional area is going to be the cross-sectional area of the larger jacket, larger pipe, minus the cross-sectional area of that inner tube. That's going to give me the cross-sectional area of flow for my water. So the average velocity of my water is 2.168 pound mass per second. That is divided by that cross-sectional area I was telling you about, which can be calculated and determined to be 0.00997 feet squared. And that is multiplied by the density of my water at my bulk temperature, 62.3 pound mass per foot cubed. Carrying out that calculation, I get an average velocity of my water of 3.49 pound mass per second. No, velocity. That is 3.49 feet per second. Great. Now I have the average velocity of my cooling fluid. I already knew the average velocity of my benzene. So now I can use those values to calculate both my Reynolds number and use the information I already knew to calculate my Prandtl number. So let's do benzene first. For our benzene, our Reynolds number is equal to, of course, rho v d divided by our viscosity. So our diameter is 0.0621. I believe that's what I wrote. Yes. Feet. I know that it's moving at 5 feet per second. I'm going to go ahead and convert that based on the viscosity values that I'm given. 3,600 seconds in an hour multiplied by the density, which is, 53.1 pound mass foot cubed. And all of that is divided by 1.16 pound mass foot hour for our viscosity. Carrying that calculation out, so Reynolds number for the benzene is equal to 5.12 times 10 to the fourth. So we are definitely turbulent regime. Right, we are definitely in the turbulent regime for our benzene. While we're here, we'll just go ahead and calculate the Prandtl number for our benzene as well, which is the specific heat times the viscosity of our fluid times the thermal conductivity of our fluid. I'm not going to write out the units this time. 0.435, 1.16 divided by our thermal conductivity, which is 0.089. And here I get a Prandtl number of 5.67. Again, this is a liquid, and we were told in one of our last lectures that typically for liquids our Prandtl numbers are greater than 1. So intuitively that makes sense to us. Now we can do this for our water. Here for the Reynolds number of our water, we need now to calculate an equivalent diameter, because again, our water is flowing in the outer jacket of our heat exchanger, and so we can't simply use the diameter. We need to use our hydraulic radius, or excuse me, our hydrodynamic radius. No, excuse me. Let me get this right for the third time. The hydraulic, I can't spell either, hydraulic radius, which, if we remember, is the cross-sectional area of flow divided by the wetted perimeter. Okay, if I do that calculation, I get a hydraulic radius of 1/4 of 0.0613 feet. So that fourth is going to go away, and I'm just going to end up with what we can also call an equivalent radius, or equivalent diameter. So DE is equal to 4RH, which in this case is equal to 0.0613 feet. Okay, let me plug my values into my equation. So density, 62.3. The velocity that I just found, 3.49. Again, I need my conversion factor based on the units that my viscosity were given to me in. And now I have my diameter, 0.0613, or my equivalent diameter in this case. All of that is divided by my viscosity, which is 2.34, giving me a Reynolds number of 2.15 times 10 to the fourth. Again, well within the turbulent regime. Okay, that's good. That tells us exactly what heat transfer equation we're going to use. While we're here, we're going to calculate our Prandtl number. That's going to be 1 multiplied by our viscosity divided by our thermal conductivity. And in this case, for water, I get a Prandtl number of 6.76. Again, greater than 1. Water is a liquid here. So intuitively, that makes sense to us. All right. Moving forward, we are going to do a first approximation of HI and HO with no viscosity effects. So for our benzene and for our water, we have the following equations. And for our water, we have HO, DO, divided by the thermal conductivity, and then the same equation on the right-hand side. I mentioned in the last lecture video that the Cedar-Tate equation was simply the Dietz-Boelter, I believe, is the equation name, the Dietz-Boelter equation, but with the viscosity correction factor. So I do not have a viscosity correction factor, so this is the Dietz-Boelter equation. But in either case, I can use this equation to calculate the convective heat transfer coefficient on the inside of my pipe, as well as the convective heat transfer coefficient on the outside of my inner pipe. I know my Reynolds number, I know my Prandtl number, I know the inside diameter, I know the outside diameter, and then of course I know my thermal conductivity of both the benzene and the water. So if I plug, let's just do it for the benzene. I won't work it out for the water. So HI is equal to 0.023 multiplied by my ratio of my thermal conductivity of my benzene, which is 0.089 divided by the inside diameter of my tube, 0.0621. And that is multiplied by my Reynolds number of my benzene, which is right here, 5.12 times 10 to the fourth. That goes to the 0.8 power, and then my Prandtl number is 5.67. Whoops. 5.67 to the 1/3. Again, this ratio here is K divided by DI. So if I do my algebra correctly, I should get a convective heat transfer coefficient on the inside of my inner pipe of 344 BTUs per foot squared hour degrees Fahrenheit. Right, that makes sense to us. The units on K here are BTUs per foot hour degrees Fahrenheit. We divide by a foot. We should get BTUs per foot squared hour degrees Fahrenheit. We can do the exact same thing for our water to calculate the convective heat transfer coefficient on the outside of the inner tube. Doing our algebra correctly, we should get a number of 691 BTUs per foot squared hour degrees Fahrenheit. Okay. So those are our two convective heat transfer coefficients. Based on this first approximation where we have neglected any type of viscosity effects. So having any information or knowing anything about benzene and water a priori would tell you that in fact you probably don't need to account for any type of viscosity effects, given that both of these are what are considered low viscosity fluids, where their viscosities are around 1 or less than 1 centipoise. But we can go ahead and try to account for the viscosity effects and see how that changes our answer, and kind of prove to ourselves that we don't actually need to correct for the viscosity effects that would be present if we were pumping something like a high viscosity oil, for example. This will also allow me to introduce a new equation that again could be helpful moving forward when solving heat transfer problems. So, for us to be able to calculate our viscosity correction factor, which is the viscosity in the bulk divided by the viscosity at the wall raised to the 0.14 power, we need to know the wall temperature. Right? Based on the information that you have been given in this problem, you do not know the wall temperature. However, with a couple simple assumptions, we can estimate what the wall temperature is based on the temperature difference between the hot and the cold streams. So for this particular scenario, if we neglect the resistance of the wall, this is something that I alluded to in an earlier video, that oftentimes we will neglect the resistance of the wall, given the fact that the heat transfer process is typically governed by that convective heat transfer to or from a particular surface. If we neglect that wall resistance, meaning the thermal conductivity of our wall approaches infinity, we can calculate the wall temperature. So for heating, so in this case this would be for the water, or we can have a case for cooling, so this would be for the benzene, since it is the fluid that is being cooled. The temperature of the wall is equal to the bulk temperature of, in this case, the cold fluid, plus this delta Ti term. And the temperature of the wall for the cooling, or the fluid that is being cooled, would be the T bulk of our hot stream minus this delta Ti term. Here, our delta Ti, our delta T sub I should say, delta T sub I is equal to 1 over the convective heat transfer coefficient on the inside of our pipe, divided by 1 over the convective heat divided by 1 over the convective heat transfer coefficient on the inside, plus the inside diameter of the pipe divided by the outside diameter multiplied by the convective heat transfer coefficient on the outside of the pipe. All of that multiplied by the temperature difference of our bulk. That is the temperature difference between the bulk hot stream temperature and the bulk cold stream temperature. So this term equals the bulk temperature of the hot minus the bulk temperature of the cold. Okay. So we are going to use this equation. I'm going to use the benzene. Doesn't really matter, but in this case we'll use the benzene to calculate or estimate what that wall temperature is. So the first thing we need to do is calculate our delta T sub I, which is 1 over, I believe I had 344, excuse me. 344 divided by 1 divided by 344 plus the outside diameter of our pipe, 0.0621, the inside diameter of our pipe divided by, here is where the outside diameter comes into play, 0.0729, and that is multiplied by the convective heat transfer coefficient on the outside, which is 691. This results in a delta T sub I of around 28.1 degrees Fahrenheit. as I am using the benzene stream, which is the stream that is being cooled, to calculate this delta T sub I, I need to subtract that from the bulk temperature of my benzene stream to get an estimate of my wall temperature. So the bulk temperature of my benzene stream was 110. Subtract 28.1, and I get a wall temperature of 81.9 degrees Fahrenheit. Now what do I need? Now I need my viscosities. So viscosity of benzene, viscosity of water, both of these at 81.9, at 81.9. For the benzene, I get 1.45 pound mass foot hour. And then for my water, I get 2.06 pound mass per foot hour. I can use those viscosities at my wall for my different fluids to calculate my correction factor. So my correction factor, let's do it for both the benzene and the water. We have 1.16 divided by 1.45 to the 0.14 power. That is equal to 0.969. This is for my benzene. And I can do it for my water, so 2.34 divided by 2.06 raised to the 0.14 power, and from that I get 1.018 for my water. I can then use that viscosity correction factor. I can come back up here. Right? I can put my viscosity correction factor onto my Dietz-Boelter equation, making it the Cedar-Tate equation. From that, I can calculate what we'll call an updated HI and HO. So using that viscosity correction factor, we get an HI of 333. That's why that number was in my head earlier. BTUs per square foot, hour, degrees Fahrenheit, and HO equal to 703 BTUs per square foot, hour, degrees Fahrenheit. So this is with viscosity correction factor, and this is without my viscosity correction factor. As you can see, the numbers do not change significantly. I can go back. I can use, let's keep our colors consistent. I can go back, I can use these values for HI and HO to calculate my wall temperature again, or calculate an estimate of my wall temperature again. If you go through that exercise, you'll see that the wall temperature you calculate is not significantly different than the 81.9 degrees we calculated earlier. I believe it's around 81.5 or something like that, indicating that solving this problem and not including a viscosity correction factor is acceptable, again, because these fluids are low viscosity fluids. The last part of our problem asks us to calculate an overall heat transfer coefficient based on the outside surface area of the inner pipe. So let's go ahead and do that. We know that our overall heat transfer coefficient is equal to 1 over, in this case we're basing it on the outside area, times the sum of our thermal resistances. So for our particular scenario, what does this equation look like? We have 1 over HI. That's multiplied by the ratio of our diameters on the outside and inside, plus the resistance due to the wall. Our outside diameter divided by our log mean diameter. This log mean diameter is calculated exactly the same as the log mean radius is calculated. And then we have our last term, which is our convective heat transfer coefficient on the outside of the inner tube. All of that's on the denominator. We have 1 on the numerator. We're going to stick with our assumption that we had earlier, where we're going to neglect the resistance of the wall. So let's go ahead and get rid of that. Again, when kW approaches infinity, that term approaches 0. And we're left with a simplified equation. 1 divided by 1 over HI multiplied by the ratio of the outer and inner diameters plus 1 over HO. Okay, I'm going to take my updated parameters, plug those in. So 1 divided by 1 divided by 1 over HI, which is 333, multiplied by this ratio of my diameters, the outer 0.0729 divided by 0.0621 plus 1 over the convective heat transfer coefficient on the outside of my inner pipe. If I do my algebra correctly, I end up with a value of 202 BTUs per foot squared hour degrees Fahrenheit. So again, our overall heat transfer coefficient based on the outside surface area of the inner pipe is 202 BTUs per foot squared hour degrees Fahrenheit. We can write that in SI units as well. And taking that to 3 sig figs, that would be 1150 watts per meter squared degrees Celsius. Okay, so hopefully that example problem helped solidify some of the concepts and helped show you some of the times where these equations will pop up and how to use them to solve for, in this case, the convective heat transfer coefficients on the inside and outside of our inner pipe, as well as the overall heat transfer coefficient based on the outside surface area of the inner pipe.